Kia ora and welcome to video 11 of Agile Algebra. This video is going to be led by another former student of mine, Matthew Batcheler. Matthew finished up in 2021. I had the pleasure of teaching him for a couple of years, and in that time he achieved scholarship calculus. He was an outstanding scholar and also top in New Zealand at technology. So some great achievements. He was also a very well-rounded young man. He was involved in a whole heap of other stuff outside of just academics, including robotics. This video is quite long because Matthew goes into all the details required to fully solve the problem. So hopefully you enjoy the solution. Here is the problem. It is an algebra problem, but obviously set in a geometric context. Maths that you'll need to be familiar with in this include sequences and series. Matthew does explain that part of the problem if you're unfamiliar to it. So if there's anything in this that you didn't quite understand, that's where you use resources to your advantage to go beyond the question and understand it a bit more.
Hey everyone, I'm Matt. I was in Schol Calc at Mags from 2019 to 2021, and I'm now at the University of Canterbury doing mechanical engineering, which is great. So today we're going to be tackling this problem that Mr. Walden sent me. So we've got this little arrangement of circles here, and they're sandwiched between the line y equals x and the x-axis, so y equals 0. And we have to find the ratio of the areas of any two adjacent circles. And already that gives us a bit of a clue that all the circles have the same ratio of area, which is just like, something to keep in mind when you're going through this problem. And then somehow we've got to find the total area enclosed by the circles, which is a bit crazy because they kind of go away to infinity, right? There's infinite little circles in there. So how are we going to do that? Well, first thing is to find the ratio of any two adjacent circles. And by the way, I'm just not much of an artist, so you're going to have to forgive my circle drawing abilities. So we'll start with part I, and the first thing you do is draw a picture. So we've got a bit of this, a bit of that, and here's, ooh, that's a bad start. That's not much better. Oh well, so we've got a big circle and a little circle, and for now we'll just consider two circles because we're finding the ratio of any two adjacent circles. So here is two adjacent circles. Okay, and we can label these circles, you know what? So we'll call this one circle 0 and this one circle 1. And this one's got some radius, which is going to be r subscript 0. And this one's going to be a radius of r subscript 1. Okay, now this is going to be a kind of geometric approach, and I reckon when you're dealing with circles and stuff, especially infinitely many circles, if you can do some tricks with geometry, it's really going to make your algebra easier. So what we can observe on this one is that if you look at the centers of all these circles, there's actually a straight line running from the origin through there. Just pretend that it's actually going through the centers. And then, okay, I can't rotate this page, which is annoying, but you can basically say by symmetry, which is just, you can't be bothered proving it, and it looks symmetrical, so it must be true, that if this whole angle is 45 degrees, then each of these little bits is 22.5 degrees, right? Okay, so that could come in handy, because we've actually got two centers of these circles. It's this one here and this one here, and we could draw a big line through them, and that almost looks like a triangle. So why don't we connect this, and now we've got a triangle. So could we think about what some of these side lengths are? Well, if we know this little section up to here, it's going to be R1, because that's another radius of a circle, right? Because these circles are tangent. And this one must also be R0. So that's interesting. We've got a circle with side length, well, the hypotenuse is R1 plus R0. And then we could do the same thing on the I suppose, adjacent. No, the opposite. So if this whole thing here is R naught, then this little bit here is R. Oh, that's wrong as well. It's just, oh my god. This little base piece here we can transfer across, and that is R1. So therefore, this side length here must be, we'll use black for that, this must be R0 minus R1. And then this top hypotenuse must be R0 plus R1. And then, because we've got this line that goes all the way across to here, and we know this angle down here, year 11 geometry will tell us that this angle here is 22.5 as well, because that was 22.5 over there, proved by symmetry. Or you could actually just draw out another little line, and that would be a right angle, and this would be a right angle, and you could probably make a more convincing argument. So I wonder if we can get some relationship between R0 and R1. Since we got a triangle and we got two sides, it's a right angled triangle even, that's probably worth noting, and an angle and two sides. So we could say sine of 22.5 degrees is equal to opposite, which is R0 minus R1, divided by the hypotenuse, which is R0 plus R1. Okay, so if we want to find, what do we actually want to find? We want to find a ratio of the areas. So we can maybe start by finding the ratio of the radii, and then because radius is directly linked to area, or area is directly linked to radius, we could work backwards, you know, or forwards, I suppose. So we want to find, let me just check my notes on this one. We want to find R1 over R naught. So we could really be finding R naught over R1. That's still the ratio of any two adjacent circles. But I've already done this question. I can tell you that this one is going to work out better. But if you've got this one, if you've got this one here, then it's pretty easy to just reciprocal it, and then you've got the other one. So obviously you don't have to know, you don't have to be able to see the future. It's just going to save us some writing. Okay, so we can start rearranging. Actually, one other thing I'm going to do, just so I don't have to write so much, is to say let sine of 22.5 equal the letter B, and that's just a random letter I chose that I don't think I'm going to want to use for anything else. So we got B equals R0 minus R1 over R0 plus R1. That's just from up here. Okay, so we can do some rearranging. We got B R0 plus B R1 equals R0 minus R1. A bit more rearranging. What do we want to find again? We want to find R1 over R0, so we probably want to find R1 as a function of R0. That's just going to help us know which way to rearrange. So now we can just say R1 B minus plus 1 equals R0 1 minus B. Therefore R1 equals R0 1 minus B 1 plus B. That's kind of cute, right? We've swapped our R0s for our B's. We've still got the same sort of form. Isn't that weird? Okay, so if we've got our ratio that we need to find, ratio R1 over R0, we could substitute in this, right? So let's do that. Equals R0 of 1 minus B, 1 plus B, all divided by R0, cancel, cancel, equals 1 minus B over 1 plus B. There you go, that's like half the marks right there. That was actually the hard part as well. Done. Part 1. Okay, part 2. What do we want to find? Oh, hang on, I've just made mistake, which I'm sure a lot of people did in this question, which is that they found the areas of the ratio, the ratio of the radii, not the ratio of the areas. So we got to find the area 1 over a 0. Okay, well, if we think a equals pi r squared, which gives us what? A1 equals pi r1 squared, a0 equals pi r0 squared. And we can substitute in for that, so a1 over a0 equals pi r1 squared over pi r0 squared. Cancel, cancel. And then we can take out the squared. That's r1 over r0 all squared. And we've already got r1 over r0, which is this thing here. So that gives us a1 over a0 equals 1 minus b over 1 plus b squared. Okay, almost done. One more thing that is going to cost you marks is if you've defined random variables, like we defined b, and then you forget to substitute back in what they actually are. So b is sine 22.5, which we've got over here. So let's make sure we put that back in, or it's going to hurt. So equals 1 minus sine 22.5 over 1 plus sine 22.5 all squared. Now, are we happy with that? And the answer is like, probably. But sometimes they can be sticklers, especially if this is a mock exam and Mr. Walden's marking it. Then he's going to be real, like, stingy about stuff like this. So sine 22.5, that's not really a number, is it? So if we put that into our calculator, then we get 0.3827 ... infinity. And we cannot be writing 1 plus 0.3827 1 minus. Don't do that, because that's not exact form. It's not really sensible algebra, you know? It's gonna make problems in the future for you. So we got to find some way to get sine 22.5 in exact form. And the answer for that is on your formula sheet, which is one of the double angle trig identities, which I've got written down in my notes somewhere. Here we go. So it's actually a bit of a sneaky one, because, you know, double angle usually doubles the angle, but we know that 22.5 is 1/2 of 45, because that's kind of like, we had all the way up here, this whole thing was 45, and we've just taken a little half sliver of it. And we also know, you know, sine 45 equals cos 45 equals 1 over square root 2. Ask your calculator if you don't believe me. So we're going to use this trig identity, which basically you just have to trial and error a few times, and then eventually you can probably land on the right identity. But the right one for this situation is cos 2a equals 1 minus 2 sine squared a. And look, if we say 2a equals 45 and a equals 22.5, then we've got right here our sine 22.5. Only problem is it's got all this other stuff around it. So let's do some rearranging. We've got sine squared a equals 1/2 of 1 minus cos 2a. By the way, this formula is also really useful for integration. If you've ever got an integral and it's got a sine squared in it, you can use this to turn it into normal coses and sines, which are easy to integrate. So, you know, these things are actually worthwhile. And then what is cos 2a? Well, we can chuck in our numbers for real. oh, actually, first we'll just square root it, because that's what we're after, right? Now we've got sine, what's a? 22.5 is equal to the square root of 1 minus cos. 2 times a is 45, all divided by 2. Then we can ask our calculator, what is cos 45? Or we just know it because we're such good students. That's 1 minus 1 over square root 2 divided by 2, which is equal to square root 1/2 minus 1 over 2 square root 2. Okay, so let's wrap everything up and we'll put this sine 22.5 into what we just found before, which was this. Okay, so we've got a1 over a0 equals 1 minus square root of 1/2 minus 1 over 2 square root 2 over 1 plus square root 1/2 plus 1 over 2 square root 2. No, that is wrong. There you go. We'll just double check we've copied it right, because that's where half the mistakes are. Oh look, we've forgotten a squared. It's another good way to lose marks in your Schol exam. Okay, so that for real is the end of part 1. You've done it, and Mr. Walden's given you full marks. And so now you want to look at part 2. So let's go back and read the question, because that's another reason you lose marks, is not reading the question. Hence or otherwise. In these cases, it's always hence. Like, come on, you're not that clever. Maybe you are, but I'm not. Find the total area enclosed by the circles. Which is a bit weird, right? Because there's infinitely many circles. So how do we find the area enclosed by totally infinite many things? Well, I guess we've got this relationship between the areas of circles, which actually let's just call a1 over a0 equals k, because I really don't feel like writing out this whole thing, you know, every time we do a line we have to write this. Not happening, and you'll like mess up bits. Just give it a variable. You could even say equals k, just to make sure the marker knows what you're going on about. Okay, so we could even say a1 equals k a0. The interesting thing is we haven't actually said what a1 and a0 are. When we started, we said they were, this circle was 0 and this was 1. But we could just as easily, there's my eraser button gone, there we go. Could have said this is 1 and, this is 0 and this is 1. Could have even said this tiny little 1 is 0 and this is 1. So that's kind of this whole ratio of any two adjacent things. They all have the same ratio. And that is called a geometric sequence or series, or there's a difference between them, but it doesn't really matter here. And that's a sequence of numbers where you've got a starting value, we call it 1, and then you times it by some common ratio. And then the next one in this is going to be 1/2. Then we times that by 1/2 again, and that would be 1/4. We times it by 1/2, that's 1/8, etc. to infinity. It's not very artistic, is it? Okay, so that's an example of a geometric sequence, but in this case, what we've got is a0, and we times it by k, and that gives us a1, which instead of writing as a1, we can write as k a0. And then, guess what the next thing is? Well, we times it by k, and it's k squared a0, etc. And there's this funny thing about geometric sequences, which is that if the absolute value of k is less than 1, then the sequence converges, or the sum of the sequence converges. So that's like if you added up 1 plus 1/2 plus 1/4 plus 1/8, that's going to converge to some number. Now if k was greater than 1, say it was 2, then you'd be adding up like 1 plus 2 plus 4 plus 8, which is obviously going to spiral off to infinity. But in this case, it's not. It's going to look more like if you plotted it on the axes as you had n iterations. And this is your sum, or you could call that S. That's kind of what people tend to call it, S for sum of n, steps. You'd start and then you go like that, and you'd be approaching this level line, and that is going to be your S infinity, which is your sum as the geometric sequence goes to infinity. So that's kind of the theory, and it's not that hard to apply because there's this magical formula which says that given that it converges, so this is going to go really wrong if you use it on something that doesn't converge, then S infinity equals the starting value divided by 1 minus the ratio. And you definitely don't need to derive that in the exam. Like if you go in, they'll either expect you know it, or they might just give it to you. I think there's a good chance they'll give it to you, but it's still really good to know. So A is our starting value. And R is our common ratio. So let's think about if we've got like an initial value and then we're moving in some direction, how does that apply to our little picture up here? Well, this could be our start, 0, and this is our 1, and this is our 2, this is our 3, 4, 5, 6, etc. And they've all got that same ratio. So we've got to find the starting value, or the starting area, which is just going to be the area of this one. And it happens that they've given us the radius of that, which is pretty good. Now we can go back here. God, it's getting long. We can say that, well, we can rewrite this in terms of things applicable to our problem. That's A0 and 1 minus A1 of A0. Okay. Which, yeah, I suppose a more technical way of writing this common ratio would actually be a n plus 1 over a n, where n is a natural number. But that's kind of one of those like maths things that is probably not really going to cost you points. It's still good to understand what that means. So we'll say n plus 1 a n. Okay, so A0, that was our initial circle that had a radius of 1. That'd be my worst circle yet, I'd say. So that is pi times 1 squared. Ooh, come on, pen. It's getting a bit laggy. Okay, so S infinity, which is equal to our total area. Just saying, because that was like when we added up all of the circles to infinity forever. See, they're getting smaller. So that is equal to A0, which is pi, divided by 1 minus, okay, what was our ratio again? Oh, we said it was K. That's convenient, because then I don't have to write all that stuff. And that's it. Oh, except that's going to cost us points. We haven't written it in terms of actual numbers. So that's pi divided by 1 minus, okay, what's K? I've forgotten already. You know what? You're not allowed to do this, but I'm just going to copy it. Copy. Oh, how good is that? Alright, and that's the answer. So we've done that by using our geometric sum formula, because it converges, because k was less than 1. And that's it.